So, guys, welcome everybody to Reactive Amsterdam meetup. This is the 25th meetup that we hold, which is a kind of nice number. I mean, that times 4 makes 100. So, it's a promising number. Well, first of all, I think we really have to give a big applause to our sponsor tonight, which is Xebia. Seriously, this was so much better than pizza. And this bag is fantastic, so I would like Xebia in person of Ghost to tell us something.
Okay. Hello. Well, you might know me from other meetings, conferences, but in between those, I do work for Xebia. And unlike most people, I think, remember it, Xebia doesn't do trainings alone, we actually go to customers. And I got software as a consultant. And well, at Xebia, we like to build stuff the right way, to make it work, so that's the customer. And therefore, we are a bunch of very passionate people. We want to build our quality and build the software is really what we need. And that's why I stand for and really cool stuff and organize cool stuff. I will see you again in the question.
Probably to be more detailed about the stuff they do. Really cool. Thanks for hosting us tonight. Really, really cool. We have another micro celebration to do tonight. Just like 2 days ago, this media reached 1,500 people. That's a lot. And so I looked at how it went with the growth, and it went more or less like this. So it started in October 2015. So that's what, 2.5 years. And the growth was almost like sort of linear. It's interesting to see that the summer breaks, the maybe you organize a meetup for 2 months, then also the signups don't grow. So it really means that if the meetup grows, then we really are doing cool stuff. And then you have to keep that going, otherwise it slows down. Probably nothing extraordinary, but yeah, I think it's a real good achievement. We are a lot of people, right? So that's great. Anyway, let's come to tonight's topic, which is yeah. For once, we're going to go a little bit deeper, because we usually stay on application level and tell how to build, resilient stuff, scalable stuff, but then we rarely touch the side of how you actually run this stuff. And so tonight we're going to look closer at how we can combine all the stuff that we usually talk about with these two guys here, Docker and Kubernetes. And so we have 2 talks. The first one is actually given by myself also, together with Adam from Software Circus, which I'm sure you have been to once at least. Yes? So we teamed up and we have a talk for you guys. It's going to be, not too polished. It's really like developer shares with developers kind of thing. And then we have another talk from Roman from the site. They're building a fast data system. So lots of data coming in, streamed really fast, processed, and then going out somewhere. And this blends, well, Roman is going to tell us how this blends with Kubernetes and all these other things. So you guys enjoy tonight. Hey guys. How you doing? Yeah, so cloud native Akka and Kubernetes, the holy grail to elasticity. Lots of buzzword suggested by a real good friend of mine sitting right there. If his title doesn't fit the slide, it's his fault. But I think it's a great time. So, we start from where we usually start, the reactive mining desktop. You probably all know it. It's this thing that's been around for a few years already. That specified a little bit some values that our service should comply with. In particular, starting from the bottom, we see that, well, what it states really is that a message-driven application enable us to build elastic and resilient apps that allow us in turn to be responsive at all times. So, for instance, resilient means that we are able to be responsive also in the face of failure. If our application fails, some exception, whatever it fails, well, we should still be able to respond, maybe in a degraded way, in a reduced sort of set of responses, but still respond. And elastic, elasticity, we all know it, it's really crucial in nowadays services, because imagine that you are Amazon, so you probably have a seasonality of traffic. Let's say Black Friday, you have more traffic, or maybe for Christmas, or things like that. Maybe you are a bank, you are EMG, and then you have, I don't know, payday at the end of the month, where you have a lot more traffic and a lot more things to do. So what you want to do nowadays, where everything runs in the cloud, is you want to be able to scale up and down accordingly. You never want to use more resources than you should use, because Amazon and Google send you a bill at the end of the month, and Azure too, by the way. So these traits here, elastic and resilient, really define reactive applications. And tonight we're going to focus a little bit on the elastic side. It comes from a curiosity of mine, so in the next couple of slides we're going to see what we put together in order to achieve elasticity. We have a lot of code to show and live demo later, so I'm just going to go a little bit, not too deep in these concepts, just not to waste too much time. So, quick recap, stuff you already know, I'm quite sure, but actor programming is the cornerstone of reactive systems. For instance, Akka is this toolkit that lets you do actor programming with Java or Scala. There's a .NET version of Akka. There's Akka.js lately. But it all boils down to using actors, where actors really are this a small unit of execution. So an actor is not like an object that you are used to think about in Java, but is some sort of entity that can only communicate with other actors via asynchronous messaging. So it's like they send emails to each other. You can see it like that. And what this enables, how does this enable scalability and therefore elasticity? Think about Amazon's example before. Is because when I can send you an email, it doesn't matter that I know where you are. So think about it, if you have my email address, you don't need to know whether I am in Amsterdam or in Japan. You send an email to that address and I'll receive it. With actor is the same thing. And in one or two words, this is called location transparency. At the moment where you don't need to know where your actor is, you don't need to know his IP address or whatever, because the system takes care of that for you, then you can just take your actor, the way you execute it on your local machine, and move it somewhere else on another node on your Amazon cluster, which is maybe in the Philippines. It doesn't matter. And the actors will keep working the same way as they used to do on your local machine. This is, in very short, the cornerstone of scalability using actor programming. And so, what I wanted to achieve is, indeed, try and create a small thing that could display these elastic capabilities. And so, what I have built, which you are going to see in a little bit live, I created this, this little program that has an input source. So, I have this little actor whose only task is to send out jobs to execute. This actor also embeds a small HTTP server that can use to tune the traffic. So at some point, I will decide that this input source needs to be a lot faster and need a lot more jobs, or maybe slow it down, and see how the application responds. So this input source sends jobs out. What follows is a router. This router receives one by one all these jobs that come from the input source and distribute this load across workers. These workers, these are all actors. Everything, every circle you see is an actor. These workers will receive a job, process it, and send a response to the router when they're done. Now let's look a little second what the worker does. Essentially, the worker does this. Receives a job, then it's a simulation, so simulates some CPU-intensive workload, and maybe after 2 seconds or something, responds to the sender that this job has been completed. What this enables us to do is that the sender knows when a job has been completed. And so by looking at all this completion that comes, the router can calculate how much power it needs. Like how much power I'm using now, do I need more power? Am I using too many actors, too many workers? Do I need less power? The router is able to do this kind of calculations. So what comes next then is another actor, there it is, we call it scaling controller, that the router can talk to in cases, for instance, when it detects that we have too little power for all the amounts of jobs that we need to process. Then the router can just send an email, a message to the scaling controller saying, please add a node. At this point, magic. We will see later. Another worker will appear, and the router will be able to deliver jobs to this worker as well. This is in essence what we are going to use tonight for our examples. And of course, at some point, maybe the router detects that we have too much power because the input source has slowed down. And then at that point, we will ask the scaling controller to actually scale down, and boom, we'll see that maybe one worker goes away. So this is what we want to achieve. In real life, those workers, they might be instances on AWS. But this is the example that we're going to work on. So with this ability to add and remove dynamically power on nodes, then we have reached something that is really elastic. Very elastic.
Are you assuming worker doing the same job?
Yeah, good question. The question is if I'm assuming that these workers are all doing the same job. And yes, in this situation, yes. They are doing the same job, and each worker can process one job at a time, and also they take a fixed amount of time, always the same, to do that job. So these are my assumptions. Really, really good question. Okay, now, the next step is you can run all this on your machine. But what if I want to run it on separate machine? So that's distribution. Well, Akka, this toolkit comes with a component, with a tool called Akka cluster. And I'm not going into any detail here, but Akka cluster, just know that it provides you with a membership service where you can make your one node, which is the leader, aware of whatever is happening if another node is connecting to it, or if another node is leaving it, is leaving the cluster. So this is a bit of a state machine where each node can be in one of those states, can be joining, can be up, can be leaving, and this, it's all dynamic. So you can add node, remove node over the cluster. And you personally don't need to work too much with this detail, but you can react to these events. There we go. And well, just one slide to show that, again, in this case, if you remember, at some point, the worker sends back to the sender the completion of its job. If you remember what I said earlier about location transparency, this code here that you have written to make your worker function on your same JVM on your local computer, well, this address has changed underneath. So Akka knows that now this address here is on another machine somewhere else on the network, but you don't need to know which one it is, because this code will work anyway. So this is the power of this actor and location transparency. Yeah, that's good. All right, so we have got everything set up. We have our little example app, our little jobs, our little workers. Now the only question that stays is then how to create nodes. When the worker asks the scaling controller, give me more power, then who is going to provision that JVM? And this is where it gets interesting for tonight. We chose Docker and Kubernetes as a way to help us out with this task. And how many of you have read actually the Divine Comedy or know about it? Yeah. The third part. Yes, yeah. So those, well, it's one of the Italian literature masterpieces. And those two guys are Dante and Virgil. And so what happens is that this was written in like the 13th century or so. And so Dante, the guy in the red coat, he's actually going through hell, like literally. Seeing all the monsters in hell and people suffering and the devils and stuff. And that guy there with the white tunic is Virgil. So he sort of guides him through hell. And so I'm totally the red guy, super scared. And so I needed someone. And that someone is Adam, who came and guided me through all this devil's madness. So I think nobody better than him can take this from now on. So please welcome Adam on stage.
Fabio, that was the best introduction ever. Awesome. So, hi, I'm Adam Chandler. I work for Container Solutions as a consultant, and well, much of my work is making things work on top of Kubernetes. And I was hearing a lot about Akka. I'm a Java developer background, but somehow never really got around to using Akka for anything. So I was very interested in Akka. Fabio was interested in Kubernetes, so we teamed up to do this in the demo and talk. So why? First of all, why is it even interesting to run Akka clustering on top of Kubernetes? So by default, Akka is something that helps you organize work inside a JVM. You don't use a thread for every single thing you do in parallel, but actors can organize the work much more efficiently, which is great. So that part doesn't really touch Kubernetes. But then there is this part of Akka called the clustering, where using the fact that the actors don't really need to be on the same JVM, Akka clustering can spread them out over different JVMs. And you could be, and this was invented in the times where companies usually had a whole bunch of JVMs running all around the place, and then you wanted to run workers on top of these JVMs. But the world has since changed a bit towards the JVM not really being your base infrastructure. Your base infrastructure is usually, well, from the public cloud providers, you get virtual machines. So that's your baseline. You pay for virtual machines, so you need to deal with actually spinning up and shutting down virtual machines. And Akka clustering doesn't help them. So, and another concept that came into play is containers and container orchestration. So how many people here have worked with Docker? Okay, quite a lot. That's not surprising. And Kubernetes or Mesos or Docker Swarm, also quite a few. Okay. So the point here is that these days, the trend is becoming the default way to package applications as Docker containers. And once you do that, the whole, and run it on a container orchestrator like Kubernetes. And once you start doing that, there is an overlap between Akka clustering, what that does, and what Kubernetes does for you. So besides just making Akka clustering work on Kubernetes, we also explored a bit on what makes sense and how does this interaction really work. And we took it to the extreme of making it work in the Kubernetes way, which means that's what Fabio said about assumptions, that one node runs one worker actor and that does processes one job at a time. So to make it more simple and make it a bit more like the usual way you do microservices on top of Kubernetes, you basically spin up a Node.js server and that executes some requests. Of course, it doesn't do one request in parallel, but that we even simplified it a bit more. But we don't spin up many actors over many nodes. We don't mix the actors with the nodes. We do one actor per one node. So why Kubernetes? Because it can provision applications by running Docker containers over a cloud infrastructure. So Kubernetes is built to work on clouds. It can provision, shut down, and start up virtual machines, and also make your applications not care about that. It provides resilience by health checking your application and restarting things. So again, something that the clustering could do, we chose to do that with Kubernetes. Well, but that's actually not really part of the demo. We focus on the elasticity. And then probably the most important thing is the mainstream adoption. So Kubernetes as a target platform is exploding. It's really explosive growth, and any application platform these days needs to consider, okay, how do I work on Kubernetes? And we saw that in the Akka world this is not discussed that much, so it's a good topic to explore. It's also tech agnostic, so you can run on the same platform other things than Akka, which is if you consider it compared to a world where you run many JVMs and then things on top of JVMs, then you can on top of Kubernetes be more flexible in what workloads you run. The big cloud providers now have, all three of them are either have or are building native Kubernetes support, like giving you Kubernetes as a service. That pretty much shows the growth of Kubernetes. It means that soon, once Amazon, like Azure is in like beta phase with Kubernetes, and Amazon are in some closed preview phase, and Google already has it in production. Once Azure and Amazon catch up, you can build applications for Kubernetes and just natively run it on any public cloud and just jump between the public clouds with an application that's on Kubernetes. So that's ensuring a long future for the platform. And it's also completely open source, open governance with the foundation and everything. It's a really strong open thing that is now all the big players are on board and guiding the project. So there is no way just one player hijacks it and Google says, oh, we do this because it suits our business plan. And finally, Kubernetes has a really, really nice API. So all the provisioning stuff it does is very easy to do programmatically. And that's exactly what we did. We didn't just spin things up, but we also have the Kubernetes controller there that does it for us, and it's very simple code and no big deal to actually do something that was quite complex before. As lots of people know Kubernetes here, anyway, I didn't plan to go into the details, but for those who don't know how it works, quite a simple model on the high level. You have a bunch of virtual machines, which is a variable amount on a public cloud where you can easily spin up and shut them down. All of your virtual machines called nodes in Kubernetes language will have a Kubernetes agent called a kubelet running on them. And then there is a Kubernetes master that knows the state of the cluster, knows what the state should be of the cluster, and is constantly reconciling the state that should be with the state that actually is on the cluster. So when it sees that you told it to run 5 instances of your application, and it sees that there are only 4 instances, and let's say in this case I have a main page here, and it's You told Kubernetes to run 3 main pages, and right now there are 2 because one has died or never started yet. Kubernetes, the control loop in Kubernetes, will see that and will launch a third one. And which node it will launch that third one on, you don't know and you don't care. You can kind of influence it, but by default you don't know and you don't care. And there is a virtual networking between the nodes. So for your applications, each of them being Docker containers, for your applications, it absolutely doesn't matter. They see all of them get an IP address and can talk to each other as they want. And then the master server, actually the heart, is an etcd database, which is a distributed database which holds the cluster state. And besides that, all the components are stateless. There is an API server with which you can alter the state of the database and what should be running on the cluster. There is a controller manager that is doing these control loops and reconciling the state of the cluster with the state of the etcd database. And there is the scheduler which actually decides when something needs to be started up. The scheduler decides which node should be started. Because of course, in the end, it does matter because you don't want to start everything on just a single node because they're probably not full and the others are empty and you're still paying for them. Yeah, so that's the basics of how Kubernetes works under the hood. And this is the language of Kubernetes from which we actually want to simplify this slide, but anyway, so we don't use all of it here. The important part is you launch an application by specifying a deployment for Kubernetes. The deployment object tells Kubernetes run 5 of my front-end containers. That's pretty much it, and it can perform. It will keep those 5 up and running, and it will do rolling upgrades when you change the deployment, and it will also health check your application and kill a unhealthy instance and restart it. And what your application is really comprised of are pods, which in the Kubernetes world, you can actually run several containers together to form a pod, which is for special cases when you're not running just one container all the time. Is the special case when you have something like a monitoring agent running next to your front-end container. And that monitoring agent will always be started on the same node together with your front-end on that, like they share disk and networking. But that's not going to be interesting for our talk today. We launch pods, and the pod is one instance of one application. And finally, if you launch many instances of the same application, you somehow have to be able to address them. And all of them get IP addresses, but that's not always enough. You can create a service that will have a stable IP address, will be registered in the cluster DNS. So we'll be able, so the service name frontend will be able to reach on the DNS name frontend. That's it. That's how simple it is. That will resort to a stable IP address, and anybody talking to that IP address will be load balanced between these pods. That's a very simple service discovery load balancing mechanism. With Akka clustering, we will not entirely use it, but we will use it a bit.
So, sorry, can I ask you a question?
Yes.
About this simple service discovery. How do you manage ports?
Yeah, so you tell the service which port to expose, and then what pod port to forward that traffic to. But as all the pods get virtual IPs, like port management is not really an issue. So all these can have port AP for web traffic, for example. You don't need to be thinking about, oh, will it clash with something else? No. Even if this pod happens to start up on the same node as this one because of the virtual networking, ports will not clash.
You don't have a problem with port unification? Like a single port you have to, for whatever reason, have a unique port? So the
single port has
unification problem. So basically you need to pick up a unique port and being able to connect to unique port for whatever reason. So as imagine like you, for example, I'm using Docker Compose. So maybe it's too much detail. So I'm taking to my Compose file, internal port of the Docker and external port where I'm mounting to. Yeah. So then it will map to my hosting network with all the ports.
No, let's take the top idea.
I'll
ask two outside of the.
Sorry.
But a good question. Just let's have a
Marcus question.
Yeah,
I just wonder why you use exactly the same front end. It would be exactly the same because of the front end.
Yes. I'm just using it as an example.
It's just an example.
In our case, it will actually be a completely separate another presentation. In our case, it will be Akka master and Akka worker process. Yeah, so back to here. Basically, this part will be running as an Akka master pod, and these will be Akka worker pods in the demo. And I have a even nicer picture showing that. So if we look at it, so here we have the router and the controller, which will be part of the master, and the worker actors, part of the workers, obviously. And that's mapped to container/process, or actually pod. It should be pod here. This is the Akka master pod. You will see this stuff in the demo in a moment. This is the Akka worker pod and another Akka worker pod. And in Kubernetes, so this is the interesting part that I need to explain. So in Kubernetes, there is this concept of the deployment that I said, that the deployment keeps running a number of pods for you. You could just start pods on your own, but then nobody actually keeps them alive. Actually, there is a feature to restart them for those who know Kubernetes and will now raise their hand. But let's just say that the deployment is the thing that is making sure there is enough pods, or the right amount of pods running. So we use deployments in this example to make things easier for ourselves. Because if we would not use deployments, then making sure there is this one Akka master pod running would be harder, and scaling the workers up and down would be harder, because we have an Akka worker deployment created in Kubernetes, and we will be changing how many workers should it manage, and that will scale the workers up and down. If we didn't have that, we would have to do our own accounting of what pods are running right now and which one decide which one to kill when we scale down. Just a bit more logic would move into our application instead of letting Kubernetes do it. When I show the demo, it will become a bit more clear. I see this. Okay. And we'll maybe come back to this slide then. Yeah, I think that's the. Oh, yeah. I will show this slide also during the demo. That's okay. So, right. Fabio, how do I? How do I get to the console? Just there. I recorded. Maybe. Yeah.
Yeah.
Good. All right. Let's do this.
What's the EU for emergencies?
All right. So right now we have nothing running on the cluster. I will do a kubectl is the command line utility for Kubernetes. And in this window, we will watch kubectl get deployments, pods, and services.
Is the font comfortable?
Yeah.
Font size? Yeah.
Could we turn that on?
We can make this a bit larger, a bit smaller.
Sorry, I have a question about the architecture. Because you said you choose the deployment as a
Yes.
type of thing. But what about for the worker using the job? Because then the router could just send things from how it is now.
If we go into jobs, then it would not be really Akka clustering anymore. Akka clustering assumes that the JVM pedal lives for a while and doesn't just start up to do a single job and shut down. That would be a whole different architecture. Completely valid one, I've done that, but this is now more like finding that space between like the Akka world and Kubernetes world.
I have a question. So, in case of Akka cluster, nodes can be homogeneous. They can be identical. You can send requests to. You don't know what worker is or master is. It's master of architecture. I wonder if Kubernetes is the same. Like you can treat each node as master.
No. So the question is that in Akka clustering, you can do different types of, like all the nodes can be the same, can be master, can be worker. Now in Kubernetes, there is a special master which you could theoretically run on the same node. You could run the master component like this way. You could allow scheduling user workloads on the master. But the default production setup of Kubernetes is that you don't, that you just keep the master separate, because that itself, if the master would be overloaded by user workloads, then you're screwed, then your cluster is fine. Yeah?
So it's multiple masters, yeah?
So now in this demo we are running on, what's happening here? One screen down. Screen down.
That was the live drawing.
It's high available, so.
Well, yeah, that's good.
It doesn't run on Kubernetes.
Yeah, probably. Okay, no idea about that. Okay, now it's killing it. It's health check failed and
Nobody was looking at the screen.
Such a bunch of nerds.
Okay, so in this case, we are running this demo on Google Container Engine, which is a managed Kubernetes provided on Google Cloud, which means we have zero access to the masters, we can't even see the exist. So if I do kubectl get nodes, I can see our two worker nodes running, and these are not the Akka nodes. So Akka nodes will be running on top of this, and then workers will be running on top of that. These are the virtual machines that are currently provisioned for this Kubernetes cluster. And we don't normally in the Kubernetes cluster that isn't Google Container Engine, you will here see the master nodes.
So
we could mix
if
virtual
you run it in your own infrastructure, can you have multiple master nodes just for payload reasons?
Yes. Yeah. The master is highly available. Yes.
Okay.
So in this case, when you run a Google Container Engine, you don't care. They do it somehow, and you don't know. Okay. So. So first I will do the demo by manually setting everything up so we get an idea of what's going on, and then we will switch over to automatic mode. So Fabio, we have the resources here. Yes, to just show you that. So what we will do, we have a Kubernetes YAML file. Do we have the latest thing? Okay. So, we have a Kubernetes YAML file which describes our application, the master part. We will be using the same Docker image for master and worker. They're both compiled into one jar file. We just use environment variables, which is to switch between a Akka node being either worker or master. These are all things for improvement there, but this is how it works right now. So what this tells us, this defines a deployment with one replica. We will only be running one master, and then there is a template for each of the pod branches, of which the number shall be 1. And the specification for the pod is that the image is our image, and the environment variables passed to it. The role seed means that it's becoming a master. We also pass in what image it should use for the workers, which is the same as for the master, as you can see. And we say use Kubernetes false, which means it will not automatically provision nodes. It will try, but it will be a no auto, and it will not start up any workers. And it will open ports 2551 and port 8080. And then we will also create a service for the master so we can access it under a stable name called Akka master. So this service, as I shown on the presentation slide here, so this is the service that load balances between one single master node. The important part is that it will create a DNS name for the master. And that's important because Akka clustering requires us to create a configuration, and it will need a host. It will need to know the hostname to be able to accept connections. Akka clustering needs to know the name under which this Akka node is exposed to other nodes. And that is not the same as the host name, but it's the name under which you register it in a DNS server. And that is because it's software-defined networking. We just do it with this service. We register it that the Akka master service always points to the node that is labeled cluster 1 with role master. And if we go up here, we can see that our deployment is labeled with cluster 1 role master. These are just random things we make up for labels, and that's how the service is built into the deployment. Because we have this service, we know we will be running on Kubernetes, we know we will create this service, we can just hard code this stuff into the configuration and say the host name will be Akka master. For the worker nodes, it will be different. For the worker nodes, we don't create a service to make things simpler, because the worker nodes actually have to find the master. So there needs to be a stable name. And that's configured here. So the seed node is always this address. So this Akka cluster Kubernetes, this is just a hard-coded thing. And here is Akka master 2551. So
Akka cluster Kubernetes is the name of the actor system.
And the node on which it is running is called Akka master. So this needs to match the DNS name on which the master is exposed. This is a bit of playing around until I figured this out with Akka clustering. And for the pods, we just pass in the IP of the pod. So to the pod, the hostname can just be the IP. Theoretically, it could be that for the master, but then we would have to fix the IP and pass it into the configuration. So it's this way, just the master has a stable DNS name. The pods are just identified by their IP address. We could do the service thing for the pods also, or for the workers, but we just chose to keep it simple with the IP address. Yeah, so that's Akka clustering configuration. If we go back to the master YAML, also we expose the master over HTTP so we can do some control stuff. Do you want to play around with that? Fabio, to like speed up or we just go with the default? We'll see if
we'll do the default and
yeah.
tell you about some other resource later.
Okay.
But that is to tune the input source, to tune the traffic slower or faster.
Yeah, because the traffic is actually generated inside the master. There is no outside process generating traffic, it's just inside the master. So the master has an HTTP endpoint exposed, so we can control how fast the traffic is. Alright. Oh, I did this. Okay, so you can see that right now we have already the service created because we did not properly delete everything before the demo. So we will go and create kubectl. We apply the master YAML file. So you can see Kubernetes doesn't care what's in that YAML file. Like it's some kind of Kubernetes object, and you just apply the YAML file to the cluster. If these objects would already exist, Kubernetes maybe does nothing, maybe changes them. If they don't exist, it creates them. So you can see that the two services were unchanged, they already existed, but the deployment Akka master was created. And that deployment is now spinning up the Akka master pod here. So this is deployment, this is pods, and these are services. So the deployment has a desired pod count of 1, current is 1, so it's but 0 is available, 1 is available, okay, Akka master is running. Next moment we can go and kubectl logs Akka, do you have this? And we can see now that we have logs. So it's now creating jobs, filling up the queue, but there are no workers, so it's not going to process anything. So now I will go and launch a worker. We go here, now I have a YAML file for a worker. And this is the manual stuff, just to show you what really happens. So the worker will again be a deployment, with one replica for starters. The labels will be different, so they don't join the same service and don't get packets bound for the master routed to them. They get their IP address injected into them as an environment variable, and their role will be, instead of seed, will be worker. There is nothing else really that would be very interesting here. So let's launch a worker. Xebia apply. Now we can see another deployment getting created up here, and a worker already launching. You can see here it's joining the cluster, and jobs are, you see already the master sees worker amount is 1, and jobs are getting completed. So the magic happened, at least part of it.
Sorry,
Yes?
maybe I missed something, but so if it's the same Docker image, how does the worker get spin up instead of the master? So where is the configuration that launches a worker to be registered with the cluster?
It's this value here, the
the
environment variable called row,
Okay.
switches between them.
Okay.
I think we'll really split this up into two processes to make it clearer, because I was confused about it at some point.
One
Okay.
question.
Yep.
Sorry. Yeah. What if, for example, in this case, the master goes down?
Yes. Kubernetes restarts it, but we lose the whole queue at this moment, so we don't deal with that really well. I think we can make it also with resilience this presentation. We do not deal with the resilience part too well. So it is resilient in the sense that the master will get restarted.
Yeah.
But if it would have unscheduled job that it never sent to the workers, then those are lost.
So it cannot right now just go straight to full cluster once again, right?
Say again?
It will just restart, but the cluster will be lost, right?
Yes. Yes.
For example.
Because it would restart under the set DNS name, the workers would rejoin the cluster. I think we can try that actually.
There's one thing to add, that it's possible to run your master in Akka as well in clusters mode. So you have multiple masters.
Yeah.
It's possible to achieve that. So
Yeah,
You can have
exactly.
more seeds if you want, absolutely.
I don't, it's just like,
recommended to have at least 2.
yeah, I think we just, that the job generation is now in the master, maybe that wouldn't work that well, but I think it's easy to extend this to like make the master properly highly available. Let's see what happens if we kill the master right now. Yeah, pod deleted, it's shutting down. Okay, mob's no longer available. I think it restarted so fast we did not even see it. Ah no, it's just. Oh no, this is master. Why is it running if it's not? Oh no, I just typed it wrong. Yeah, it's already running. Just restarted from the 0.0. And does it know? Oh, that doesn't know the worker.
No, the worker hasn't joined.
I don't know if it would ever join.
I think
I've never tried this.
I think Akka cluster actually sets up like a unique cluster ID on start, and that's used to ensure that you're not creating a split brain event.
Ah.
So because if you had the master go down temporarily, you could spin up another Kubernetes thing that would also think it was the master, and then you could fight, right? But you have to manually kill it.
So if the worker wants to join the cluster, it will not join another cluster.
Yeah,
I would have to kill the worker to
not auto-magically, I think.
yeah. Yeah, it's immediately starting up a new worker when it sees that the old one died, and it's joining. Yeah, yeah, you were right. That's okay. So that was mainly. Oh no, I want to show like scaling up the worker. So we do kubectl scale deployment Akka worker replicas equals 5. Now you will see the deployment is starting up for workers. This is something we use heavily in our code that automatically does the spinning up of the workers. So instead of us managing our pods by ourselves, we rely on the deployment controller in Kubernetes to manage those pods, and we can just play around with how many replicas is the deployment controller supposed to run. So we just do this kubectl scale, whatever, and we can, you see jobs are getting completely real fast. Now I'm scaling down to 2. Likewise, 43 minutes, okay, so we go to Alright, so I delete the master.
In Google Container Engine, there is no automatic scaling of nodes, right?
There is.
There is?
Yes. So if this would have gone, like if we would have launched too many workers, it will spin up any virtual machines.
Ah. It's not about Kubernetes, but container engine, huh?
It's like a plugin to Kubernetes.
Ah.
And pretty much everybody's implementing it for different platforms. Okay. Build the workers. Now we go back to automatic mode. So we enable, we use Kubernetes flag to true, and we launch it. But now I will not be launching the worker YAML file. This was just for show. This is not needed. I will show it how it applies. Now the master is starting up. Okay, yes, there it is. So first we detected that the Akka worker deployment doesn't exist. And then, so it first creates it with one replica, and if it detects that one replica is not enough, then it starts scaling it up. Let's see. Should it, by the default, rate already scale things up?
So the scaling up or down, it's possible to take such an action only every so often. So like in this case, only every 30 seconds, because otherwise that would mess up statistics. So it takes a little bit to spin up a pod. So now the next run,
Yeah, there it is. Yeah.
Yes, exactly. Now we detected that we need more power. It added a new node. Just join the cluster. This is all the logs from Akka cluster. And so we see there's two. The jobs that get completed by C1 and C2. They are the name of the workers. And this is also still not enough. So in about 10 seconds, it will create again a new one.
How does it decide that?
We can show, well, it's some logic that I wrote down here based on these values that you have here. So waiting jobs in the queue, or how much the rate, how many jobs arrived, how many were consumed successfully, and things like that. It's just some logic that I wrote.
So it's not any back per short mechanism for this back pressure.
Again? No, back pressure.
Yeah.
Oh,
because that's the only way.
No, it keeps them in a queue. It keeps them in a queue, yes.
And you implemented the router from different router with Akka provides here. So you didn't use the same Akka router mechanics, which is there. Because, I mean, you implemented the full routing mechanism, just call it the router.
Well, I used the cluster pool router.
Okay. So it's a proper Akka router.
Yeah, there it is.
Just the scaling logic is also. And then there is the Kubernetes controller, which here is, for example, some piece of it. So it's using the Kubernetes client. There is a Java client for talking to the Kubernetes API. And it's, for example, here is deleting the deployment. So extension deployments, rename worker deployment, and delete on shutdown. It's deleting the worker deployment. Or on receiving the add node message, it will check if there is a deployment already. If there isn't, then it creates the, if there is already a deployment, then it will create one more replicas. If there isn't, then it will create the worker deployment. And the worker deployment is created by this Java builder syntax, which is way uglier than YAML files, but this is how you do Java, or Java/Scala. It would be nice to just template the YAML. But it's the same stuff as here in the worker YAML file. Basically, just written in Java and written in more dynamic way.
So let's
Yeah,
see,
let's
see our cluster is soon.
Yeah, it's completed a lot of jobs today. Wish it was Bitcoin mining.
Well, so we will keep doing this and adding nodes or removing nodes until it finds a stable point, which is also described in the logic that I wrote. And yeah, so if you let this run long enough, what you will see is, so we'll save this.
This one we haven't
Yeah,
this is just the communication of who talks to whom. So Akka master references the workers by IP address. It knows them because the workers first, when they start up, they go to the Akka master service, basically the DNS name, to register themselves. But when they register themselves by IP address. So the Akka master doesn't need to go to any service to talk to the workers. He just knows their IP address and then talks straight to them. That's pretty simple. The workers need the table Akka master service to be able to find the master, because otherwise they would have to know somehow the master IP address upfront. And the master also talks to the Kubernetes API server to launch new workers. And he doesn't actually need to tell the workers anything. It can just like spin up a worker, and then the worker joins the cluster, and then they join Akka cluster. So there is this 2 layers of clustering above each other.
From authentication point of view, when the master talks to Kubernetes, does it need to know credentials, stuff like that?
Yes. The service account, a service account to the API server is injected into the pod. So in your logic, you don't have to like also the SDK for the API just lets you just create a client, you don't do anything. But in the Kubernetes configuration, you can then assign roles and everything, like what can this service account do. So this service account can launch.
So I have an opinionated question actually. So if we, let's say, start...
Can we maybe let Fabio show his graph first, and then we go to the questions, and then we can do the opinionated.
Yeah.
Just let's finish first.
Just wanted to show you guys that if you let this thing here run long enough, I've done that and I've collected all the metrics, then you get to basically this, where if you look at the blue line, that's the line of jobs waiting in the queue. So when we start, and there are no workers that consume them, then this line, this blue line only grows. But this yellow line, which is what we really care about, shows us that we will step by step add more workers as we see need. And then this red line is basically the difference between jobs arrived and jobs that have been consumed in the same time window. So what we see is that when the workers reach a certain number, then we are basically burning more jobs than arrive in an interval. But then we keep it like that because at this point we have a long queue of jobs to burn. So we actually keep adding workers until we're really burning fast jobs like the queue. And as soon as this queue, blue line, reaches close to 0, then the algorithm detects that we are using too much power and scales down. And it reaches this optimal line where this queue of jobs stays steady, but at the same time we're not paying for pods that we don't need. And so this is stable for a little bit, and then you can see the green line That's the amount of jobs that arrive per window per second. At this point, I decided to slow it down, which immediately shows that we are immediately burning too much with respect to what we need. And then, you see the yellow line here, the controllers scale down and remove 2 pods and find new stability right there. So to me, this is really elasticity, the way I've always dreamt about. And yeah, guys, it's been a little long, but thanks for staying with us. And throw anything in us for a few minutes, because there's another topic.
Okay. Then probably still about something you wrote there as a note. So let's say if you are starting a new project and we're gonna use the Kubernetes, so we really need these multiple layers of clusters, or we ditch out the Akka cluster because it's just not needed. Kubernetes also supports its service, load balancing and stuff. And do we really need Akka clusters in this case?
That's a good question that we talked about. From my point of view, probably if you know that you are only going to build a job distributor like this, maybe you don't need Akka. You could just use Kubernetes on load balancer and build everything working on HTTP, for instance. There are other use cases where you might want to use Akka. If it's not just a load balancing thing that Kubernetes already provides. Akka has this thing about you can communicate back and forth with actors, so you can implement your own metrics, for instance, and maybe your own logic of scaling up and down. If the Kubernetes based it on the CPU usage, I believe. Maybe you want to use some other metrics to scale up and down.
Also, I think with Akka, the Akka clustering, you can achieve like a higher level of elasticity in the sense that if you don't mind many JVMs running all the time, then like starting up actors on top of the JVM is much faster than starting up JVMs on top of Kubernetes. So it depends on your requirements, how dynamic, how fast you want to be. But our conclusion kind of after this is that yeah, it's questionable whether you really need Akka clustering. It definitely adds a layer of complexity. It does reduce your options for like implementing your services because it needs to be Java and Akka basically, or like JVM based like Scala, Java, and Akka. So there is a trade-off you make, and you go into very much Akka land when you start implementing things this way.
I believe you shouldn't judge based on only Akka cluster. There is Akka S2, there is Akka persistence.
Yeah, that's there is no question about like Akka being a great tool for organizing things inside one JVM. So Akka streaming does exactly that. This is just about the Akka clustering. Whether you want to distribute loads over like different like physical, because everything is virtual, like different physical nodes using Akka clustering, or using just relying on Kubernetes. You can still have Akka inside your JVMs that you launch.
I want to add something to that. I think the advantage of using Akka cluster over like load balancing is actually that it's message driven. Like in normal load balancing, you do HTTP request response, so you have to HTTP request open, and then you wait for 60 seconds, and then you get a gateway timeout or another timeout that's kicks in. And with Akka cluster, you can actually, you don't have to wait. It's fire to get, and you wait until you get a message back. So it's like a message sent back instead of having the connection still open and waiting for a response. That's one of the...
Which also you can like implement it on Akka, but Akka makes it super easy. So it makes the Akka cluster makes a lot of things nicer for the trade-off of more local doing to a certain set of technology. Any other questions?
Will you share the code?
Yeah.
Probably. I need to polish some things and.
The Kubernetes credentials are for it.
We need to make a new commit that we move them.
One last question.
why did you? I guess I'm curious. Why did you choose to have like separate master Kubernetes role, or like as compared to a cluster singleton? Was that like a conscious trade-off, or like?
Yeah, that's a good question. So cluster singleton is a feature that Akka cluster offers you. So we totally didn't cover it. But yeah, I guess we could have. We just went for sort of bare bones after.
I think like also that we were influenced. We tried to like approach this from like the how we build like microservice applications on Kubernetes, right? The different processes have different roles, different code even. So like not this Akka approach is kind of like running many JVMs that have the same code and can run all kinds of vectors everywhere. And then the Kubernetes approach is that one service might be Node.js, the other might be Java and something, so that we were kind of thinking, okay, so the master is a different pod than the worker pod, so it's see where that leads us. But I think, yeah, in the end, I guess we could just treat the whole cluster as an Akka cluster and just dump vectors wherever they want to run wherever clustering runs.
Very nice. Thanks. Let's have a 5 minutes beer and then go back.